Welcome everybody. My name is Rasmus Bro from University of Copenhagen, and we are very happy to have David Broadhurst here, even though it's quite late in Perth. David has worked with omics from, well, I guess I don't know what you call yourself, a systems biologist or whatever, but you worked in this field for many years, and today we're gonna hear about basically, I guess, how we can be sure what we're measuring. As I just informed you, save your questions for the end. David will go through his presentation, and then we can talk after that. And with that, David, please have a go.
Okay, can you hear me okay?
Perfect.
Right, thank you so much for inviting me to talk. It's a pleasure to present this. Yes. So if you weren't aware from the invite, this is going to be primarily a demonstration of some software that I've written over the last couple of years and published earlier this year. It's called QCMXP, and it is for doing quality control for, it says metabolomics data, but it is applicable to any sort of data in which there's some repeat injection quality control sample. Now, a couple of disclaimers. Because this always comes up for some reason when I'm demonstrating this software. People ask me, can I load in raw data files from instruments, thermo files, waters files? This software does not do any sort of deconvolution. There's plenty of really good tools out there for doing the deconvolution. This is the second step. This is the step after deconvolution. This is where we're looking at the repeatability of the measurements that we're taking. And it's not specific to mass spectrometry or any type of metabolomics platform. As long as the data is repeat ejection QC, it can be used. I've used it for targeted analysis, lipidomics, metabolomics. It can be used for proteomics if it's of this form. So the basic data format is this format that I created called TidyMet or TidyMet QC for this application, of which is it has a GitHub page of its own if anybody wants to go and look at the details. But it's basically a two-table system, linked table, where we have, in this case, it's C18 negative data. And so we've got the first 7 metabolites listed here, and these are the peak areas. And then each sample will have a sample ID, a sample type, whether it's a test sample, a QC, or a blank, the order of its injection, and the batch that's injected. And then you can have other data in that table as well, regarding that you might use for statistics later. And then linked to that will be a peak table, which will tell you the name, maybe the molecular weight, retention time, and any other metadata that you have for each peak or feature. It has to have a unique ID and a name. Other than that, it's optional. So that's the kind of starting point for the data sets. Now, this is very much a companion piece to this paper. So if anybody is watching this on YouTube, now would be a good time to pause and go and read this paper, because if you read this paper, then most of the introduction or the theory side of things is explained in far more detail than I can possibly do in the next 10 or 15 minutes. So let's go. So I'm going to talk about some background, kind of with a historical flavor, so you can kind of get a feeling of the timeline, then a demonstration of the software itself, and then if I get time, some ideas about how I actually went about designing the software and some of the choices that I made. So if we just go back to the basics, if you like, if we look at a very simplified model of the targeted metabolomics workflow, here you would have your samples in matrix. In this case, it looks like it's blood. Then you have a measurement system, mass spectrometer, from which you get a response, which is a function of the concentration of a metabolite in that sample. This response is usually peak area or pink centroid, but let's just stick with the peak area. And then there's a calibration system in that you would inject calibration samples, standards, from which you can then calculate a calibration curve. And then the output will be an estimated concentration based on that calibration curve. So the estimate is an estimate of the concentration in the actual sample. Now, in untargeted metabolomics, we miss out the calibration step. And also for a targeted assay, you would go to a lot of effort and time to really tune your instrument and the chromatography to pick up whichever metabolites that you're targeting so that you get very clean, accurate data along with the calibration curve that you're generating. Now, what we do with untargeted is we replace that calibration curve with some deconvolution software, and then the instrument is tuned to cover as much as you can of the metabolome as well as you can, but it's not targeted particular metabolites. It's a very general purpose. And with that in mind, you're going to get some peaks that are measured very, very well and some peaks that are measured very, very badly. If we group that whole process together, we can think of it as the response is a function of the concentration of the metabolite plus some unknown error. Now, I've listed it here as an additive error. It could be multiplicative, but let's just keep it simple and say that it's an additive error. And then the quality control process is to monitor this or to measure this and determine whether a list or a number of peaks are worth continuing in your statistical analysis, or maybe you want to throw them away. Now, if we go back in time to when we were first looking at introducing quality control into untargeted metabolomics, Ian Wilson came up with this paper where the idea was that because we weren't doing any sort of calibration and we couldn't do any sort of standards to measure that instrument repeatability, if we take a small aliquot from every single sample in the study, pool them, and then sub-aliquot into a number of pooled QCs, and then inject them periodically throughout an experiment, then you can see how reproducible that metabolite is across a given run. And then you can calculate the relative standard deviation of that QC injection. And the idea being that for the US FDA, there is for a kind of publishable assay, the expectation is that your relative standard deviation would be less than 20%. So that's the kind of goal we were aiming at, so that when we assess each peak individually, we could then see to what degree how far away we're from that kind of gold standard of 20%. Now, in 2009, or a little bit earlier than that, a project called the QCMXP project was started in Manchester, and this was quite a large-scale clinical metabolomics study. It was probably one of the first studies of like several thousand samples. And so we started to investigate the use of pooled QCs in our experiments. And one of our early experiments showed us that there was actually, when we looked at the data after doing those repeat injections, that if we looked in the PCA space across a lot of metabolites, there was this within batch systematic drift, as you can see with this arrow. And then when we would do multiple batches with a clean step between each batch, there was more of a step bias across multiple batches. This is a little bit worrisome because obviously you want to have the highest quality data, and having these sort of batch effects is not going to be very good for ensuring that. What I found when I investigated this further, that often the systematic bias was something that was reproducible, or certainly something you could model. And here you can see where I have fitted a regularized spline to the data. And if you're interested in regularized splines, and this is the backbone of the correction algorithm that I implemented, there's this book here, which is where the code that I used is taken from, and it's implemented in MATLAB using the standard library. And then the aim here is that we have this regularization factor here, alpha, that if you use cross-validation, you can then tune the algorithm so that you don't overfit the data, so that you have you capture the systematic bias over time, but you don't remove the noise in the data, which would be then overly estimating or overly being optimistic of the quality of the data. So that's the basic principle within a batch. Then when we look at between batches, it's just a simple matter of aligning those batches together to the grand mean. A very simple process because all the hard work is done in the within batch correction. This is a very simplified overview of this whole process. If anybody's interested in a bit more of the maths and a bit more of a critical assessment of this whole process, if you go to YouTube and put this search term in, the first lecture that comes out is one that I gave about 3 years ago, which talks a bit more about the complexity of this sort of approach. but don't really have time to go into that right now. So this ended up in multiple papers. The big paper was the Nature Protocols paper from the Hughes project in 2011. And then there was a series of papers, particularly looking at explaining why QCs were important. And then finally, the algorithm, which is pretty much implemented now in this software, was actually first published in 2013. The algorithm for the first paper, for the Nature Protocols paper, was actually a lowest smoothing algorithm, and then I used a spline to join the dots of that smooth curve, and then I updated it to a regularized spline when I tested out various options, and this turned out to be very similar in performance, but far more efficient in terms of processing time. At that point, things kind of paused in the publication space. Obviously, I was using this software on my projects and projects that are all involved with in Manchester and then Cork and then Alberta. And then there was various people, long-term collaborators on bigger projects that asked me to help them out. And this is one of many examples of Craig Wheelock and his group. And this is a fantastic study that he published in Analytical Chemistry, a methodology for doing a kind of slightly targeted method, but it still needed correction. And this is 13 batches, I think, and you can see how that drift accumulates over time and how the algorithm can do a pretty good job of correcting that. At this point, it was MATLAB code, command line. I was the only one who was using it. It was publicly available in one form or other. Other people were generating versions of this type of algorithm and then versions of signal correction using any sort of machine learning that's out there. There's a support vector machines method. There's a random forest method. You name it. If there's a machine learning method, it's been used to try and do this correction. I particularly like the spline because it's quite transparent. You can do a very easy before and after, and I'll show you that later in the software. Where in 2017, I was invited to be part of a think tank, particularly looking at quality control and quality assurance in metabolomics. And that's where I introduced more of an idea of doing data cleaning after we've done any batch correction. And I introduced the term relative information content. And what I mean by this is the top metabolite here, you can see that that's a very good metabolite. The QC is very tight. The biological variance is a lot bigger than the QC variances, which is what you would like to see in a good metabolite. Whereas the metabolite on the bottom, you can see that the variation in the QC is equal to the variation in the sample. And this is just no biological information. There is no real point in moving this metabolite forward to statistical analysis because you're only going to find, it's only going to add rubbish to any multivariate models, and any univariate statistics are going to be unusable. Whereas up until this point, we've been very much basing all our analysis using relative standard deviation, which is the sample standard deviation divided by the mean, if anybody doesn't know. I introduced this idea of the dispersion ratio, which is the sample standard deviation of the QC divided by the sample standard deviation of the sample. This is similar to the F ratio in a non-over test, so the within group variance divided by the between group variance. But in this circumstances, I wanted to keep it on the similar sort of scale as the RSD so that they were somewhat comparable. So this is the equation that I used. And if we just look at those two examples again, you'll see at the top, we've got an RSD of 5%, which is very good, and a D ratio of 12%, which is very good. But you can see at the bottom where this is the peak that we said that was poor, but you can see that as far as the reproducibility of the method, this is very good. It's less than 10%. But in terms of the information, the biological information content, it's very, very poor. So this is where it is important to look at the repeatability of the measurement, the instrument, but also the context in the terms of what that metabolite is measuring biologically and whether that's of interest. And that's probably more of the RSD is probably more of the area where analytical chemist kind of gets obsessed about, where the data scientist and the statistician is going to be far more interested about the information content that's in that data, in that peak. So just to kind of give an overview of what a single experiment might look like in terms of that comparative relative standard deviation, if we plot the RSD for the samples versus the RSD to the QCs, you can see that for the over 2,000 metabolites that you get a distribution. Now, what we'd like is for all of the metabolites that we measure to be in this kind of area. So anything with a high RSD for the QC you would want to remove, and then anything with low information over here you would want to remove. So if you do a kind of threshold on those two factors, you can see how you can remove a lot of garbage from your data set before you would then move on to doing any statistics. And just to illustrate this is a before and after PCA plot where we've got some replicate measurements and a pooled QC. You can see after we do the QC correction and after we do the data cleaning, it goes from being very messy to a really good PCA plot with some very tight triplicates of data. And as I said at the start of the talk, this ended up in the year later in this paper, which has gone down quite well. And then yet again, things paused in terms of the development of this software any further. I was doing a lot of projects in the background, and then of course COVID-19 hit. And COVID-19 was the catalyst for me to actually think about developing this into a standalone app that people could use, and it wasn't just me doing service work for other people. And that's where we are this year in May 2024. That's when this was released on GitHub, and it's got a DOI on Zenodo, and that's where you can find it. That's a quick link to the GitHub page. And there is a bit of a guideline in a tutorial on the GitHub page, but I've intentionally been a bit hands-off, because what I really want people to do is try and play with the software and understand through our experiential learning. We'll talk about that a little bit at the end of my presentation, hopefully. So the workflow for the software is fairly straightforward. You start in the yellow, you load the data. There's a pre-filter which determines how many QCs are seen across that batch, and then you can set a filter. We usually set it at 20%. That is, we expect no more than 20% missing QCs in a given peak, or else I don't consider that peak reproducible, and the statistics that you would calculate from that QC data wouldn't be very accurate. So I do a pre-filter before we do any of the correction. Then there's a configuration settings for the actual correction algorithm, and we'll look at those in detail in a second. Then there's the actual correction engine itself in red. And then once you've corrected it, you can export the corrected data, but then you can also go and explore and visualize and filter the data, and then possibly export out a clean data set should you like. So at this point, I'm going to flip over to, if I can just escape this. Okay. So now we'll move over to the software. So when you launch the software, before you load it, for the first time, if you've never used it before you load any data in yourself, if you just click on the Config Explore button, a window pops up like this. And I've preloaded 25 single batch spectra just so people can have a bit of a play around with the software and with the configuration settings so they can start to understand how this is working. Here you can see we've got the red dots, the QCs, the blue dots are the samples, and then we've got the purple spot here, which is a blank sample. Now, just to make it easier to look at the correction, I'm going to ignore the blanks for now. So I'll click that button, which removes the blanks from the viewing. They're still there, they're just not plotted. And then you can see the before and after correction, and then you can select a peak you want to see. Or you can just randomly scroll through, and you can see that each peak has a slightly different trajectory. Some peaks don't need correcting, some peaks do. Let me find, I think if we go to 25, oh, no, it doesn't, 21. I think it's 21. Yeah, 21's a good one to demonstrate the first box here in the configuration. I have a very basic outlier detection, and the idea is, you see this red dot here, that's a QC that's been detected, but it's a poor injection, or there's something went wrong with the sample. So in order to get a really good and accurate model of that drift, you would want to erase this. Just to show you what happens if I don't have this, you can see how that how the correction curve has been skewed by that extra point, which is an outlier, and you're not getting a very good correction curve. So there's several methods. The percentile is more of the standard non-parametric outlier detection. And then the other methods are basically fitting a linear, quadratic, or cubic curve to the whole of the data set, and then looking at anything that's below the 95% confidence interval is highlighted as being an outlier. And then you can either ignore it. In the post-processing, if I ignore it, you see that data point remains there. Or you can set it to the mean values, in which case it's replaced, but it's replaced by the median value. Or you can just delete it, and then it's a missing value. So the choice is yours. You can play around with it as you like. And then for the spline, if we go to another one, which is kind of nice. So here's one where we've got quite a bit of nonlinearity. So what the spline is doing is fitting to the point. Now, if I put this to a different range, okay, you can see here where this optimizing the smoothing parameter helps determine the optimal smoothing curve. What I've done here is an interactive button where you drag this along, and you can see on the right hand side in the gray, you can see the optimal correction, and then you can see to the degree the curve fits the data when you underfit it with a median or a linear curve, and then you overfit it where it's pretty much point for point, and then your RSD goes really, really low. So that's the optimal. In this case, we're using 5-fold cross-validation. You can use multiple different optimization methods, and then Monte Carlo reps so that you can do multiple optimizations. Now you'll see that even with this, you'll see that it's not the same every time. This is a function of the fact that we're fitting a smoothing spline to very few data points. So you kind of have to play around with it and see whether you feel like you need to constrain that search area. What I've generally do is I constrain the lower limit to 0. So the worst it can do is that kind of smoothing. It can't do a point to point even if it wants to. So again, use it as in the way that you like. What I've done for comparison purposes is you've got a linear correction, which just is a basic linear regression, robust linear regression. Median, which is doing nothing. It just calculates the median, and that's the correction across multiple batches. And they're the three main methods that I'll talk about today. But spline is the one which is the non-linear method. We have another box at the bottom, which is to do with the blank ratios, but I won't go into that today. I don't think we're really going to have time. So what we do now is, once we've closed that, is it asks you whether you want to transfer the settings that you've set up there to the main window. In this case, I won't, because we've played around with it a bit too much. But you can see now that everything that was in that Config Explorer is now here. So it's ready to be used in a real data set. Now, if I load up a data set, and I'm going to use one from the GitHub page, just find it. So it's loaded in. There's 1,560 peaks. There's 24 QCs, 8 blanks, and 72 samples and 2 batches. Because this data is actually a very, very clean data set, you can see that most of the peaks have almost all of their QCs. There's a few with more than 5%. If we were to set that to 5%, you'll see that it's gone down from 1560 to 1508. So we've removed a few by being very, very harsh on the number of QCs missing per batch. So that's the starting point that we'll do. You can see here now, these are the config files, parameters that we've set. You can save that out. The reason why I've done this as a kind of editable text is so that you can save and load. So once you might have your instrument, once you've played around with it for several data sets, a set of parameter values that you're happy for that are going to be fine for most of the data sets that you process. So you could save this out and then load it in anytime you like. If you want to change anything, you can change it. It is editable, so you can just change it there. And if you've done what I've just done there and misspelt something, it will tell you what the possible options are should you go astray. So we'll leave it as spline now. And I'll set that running. It starts up a parallel processor. My laptop has 10 core processors, so it can run 10 metabolites at a time for the correction. Remember, this is correcting each metabolite individually, so it's basically going through all of those one at a time, fitting a spline, correcting. While that's running, if I open up the Peak Explorer, if it'll allow me. Just thinking about it. There we go. So the Peak Explorer is similar to the Config Explorer in that you get a before and after of the metabolites, but this time you get it across all the batches in your study, so you can see both the within batch correction and the between batch correction. In this study, we've got 2 blanks at the start and end of each batch, and then a QC every 5th. I'll ignore the blanks again. And then you can see when I press a random peak that you'll see the before and after. And you can see that kind of step difference between batches, which is then corrected as a second step of the process. And again, you can change the settings here as you could with the Config Explorer, except instead of it being sliders and buttons, you're just changing the text, and then it's showing you the optimal correction for each of these batches. Right, so now that with this is finished running, you can go and save out the corrected data if you like, but we won't do that right now. We'll just go dig straight into viewing the data. Basically, you just get a lot of visualizations. The first one being a PCA analysis. It's important to note that the PCA is done on the samples, the test samples only, and then the QCs and the blanks are projected in. This is to make sure that those QCs don't bias the PCA plot, and that all the other statistics that we might do from the PCA plot are unbiased. But you can, so if I uncheck that, it takes the QCs out and you put them back in. I can project in the blanks. I don't have any reference samples in this data set, or else you could project in some reference samples, which would be a kind of an independent test set that you could validate the correction. And then you can look at things in relation to the batches themselves. These are the 95% confidence intervals of the population, and then you can see here, if we zoom in, you can see that there's the QCs. If we zoom back out again. What's useful to do at this point before we start doing any cleaning is to do a before and after, and you can see now, this is before. We've got 2 batches with drift within the batch, and then once we've done the QC correction, the after, the drift has been removed and they've been overlaid. Don't worry about the different shapes of the population. That's perfectly normal. There's no guarantee that the distribution of each batch should be identical. There's no reason for it to be identical. But these 2 QC population distributions should be overlapping as they are here. Now, the other plots, let's do this one next. And this is the plot that I showed you previously. And we've got sample RSD versus QC RSD. And if you click on any single point, then it'll give you the statistics for each of those data points and the confidence interval of those statistics. Remember, we're not using that many QCs in these studies, so it's kind of useful to get an idea of the confidence of that statistic that you've calculated. And you can see that some of them down here are very good in terms of the QC RSD, and then have a high sample RSD, which is what you would like to see. There's another type of plot which is a bit more complicated, but actually more useful. And this is I've called it the Imperial plot because the guys at the Phenome Centre at Imperial College London were the first people to use it. And it's basically a pair of points. So if I click on one data point here, you'll see that two points have lit up. And this is one feature, and this is the sample RSD, and this is the QC RSD. So as with previously, every time you click on one, you get the pair. And this is very useful when you start doing the data cleaning, because it's really intuitive as to what effect that data cleaning is having to the data. Other than that, we have some distribution plots, and we won't dwell on those too much here for time issues. So if we go straight over to the cleaning, first up, we're basically doing a clean of the number of missing data per peak across all the test samples. So I'm saying if there's more than 25% missing values, then we're not using that peak. You can set this to whatever you like. It's up to the user. It's going to affect the missing value imputation for the PCA plot, but that's about it. And now we've got these way of filtering the data. So we've got the QC RSD, sample RSD, the D ratio, and the blank ratio. We won't be looking at the blank ratio today, but what we can do is we can set the QC RSD to that magic 20%. You could set the D ratio to something where you're getting rid of the real poor peaks, but maybe you could tighten it up to whatever you like. And then if we switch that filter bank on, you can see now where we've grayed out the metabolites which are removed. And you can see that before the filtering, we had 1486 peaks, and after we've got rid of a couple of hundred peaks by doing that. Just to show you what happens if you really crank this up, you can see that the D ratio is creating this band of data where the idea is the distance between the QCs and that line is the variable that's shifting. So if we stick that back to something a bit more reasonable, and then this pretty much draws a line, vertical line across the data set. If we look at this in terms of the scatter plot, like I showed you in the slides, you can see where I've removed those poor peaks. And if we go back to the PCA plot, you can see now that we've got an even tighter clustering. So that would be what I would be considering a good data set. And then you can save that out as a clean data set back into the Excel sheet that I've used for the input data. And that's basically it. So that's a kind of very brief overview. There's a lot of more details. I'm more than happy to give people a deep dive tutorial on another day. If anybody's interested, you can get hold of me through the GitHub page or through LinkedIn or through my Twitter account. But I think that's going to have to do for now because we're running out of time. So hopefully that kind of gave you a bit of a flavor of how the software works. So if we go back to the slides, I just wanted to briefly touch on some of the design principles that I was trying to use, because I think everybody would admit, if they look at the interface to the software, it's a little bit esoteric, shall we say. It's a little bit quirky, but it was done for a good reason. I really wanted to experiment with the idea of how we present these sort of methodologies. So there was kind of a list of things that I wanted to achieve. Well, the first one would be to be accessible. I really want this to be something that particularly analytical chemists could use, where they may not be particularly interested or happy to load R libraries in or try and install R or Python or anything like that. I have tried to encourage people to become programmers, whatever their background. Some people take to it. Some people are just too busy. Some people just don't want to. So the easiest way for people to get on board with understanding the concepts was to provide something that was a standalone app, because that was the easiest thing to install. Fundamentally, I wanted the software to be educational, because I wanted people to learn how to use the algorithm and understand what the algorithm was doing. I wanted the algorithm to be transparent. I want people to really see what any sort of manipulation of your data is actually doing to the data that is your data, and hence the before and after plots. I wanted it to be somewhat playful and interactive, so that people really felt that they could just play around with it. It's pretty much bomb-proof. You can do anything, press any button, change any setting, and it won't crash. Or if it does crash, just boot it up again, and no, it won't crash, I promise. But it also provides lots of choices. So for anything where it's something of real importance, there's always an alternative. So we have the spline correction, but I wanted to have the linear correction or no correction, so you can compare. When we're doing the missing value imputation for the PCA, it does k nearest neighbor, but it also does replace it with 20% of the lowest missing value. So anything where I can encourage playing around, changing method, changing numbers, changing options. I've tried to do that to encourage people to play with it and learn. This in turn will hopefully encourage people to develop their critical thinking abilities, particularly in this space of quality control, and really focus on trying to do one thing well rather than doing lots of things fairly maybe not so well, or one thing well and everything else really badly. There is no way I'm going to be adding on any statistical tests or statistical modeling into this app. That's why I have a standardized data sharing protocol, so that I can save this out, and then I will then load this data into whatever software I'm doing my statistics in. I might be using MATLAB, but it might be Python, it might be R, it might be another standalone app. So that was the kind of the overall things that I was going for in terms of box ticking. And then I spend a lot of time in my garage. I'm a very keen but very poor cyclist, and I have a cycling workshop where I seem to spend most of my week, at least half of my weekends, fixing my bike as much as riding it. And one thing that, if anybody who's worked in a workshop knows, is that if you have the space and the time to lay out your tools like the picture on the left, rather than keeping them in a toolbox like the picture on the right, then you know that you're going to be far more productive, and it's going to be a far happier experience. And this kind of approach is known as first order retrievability. I didn't have a term for this. This was taken from Adam Savage off the television. He's got a YouTube channel where he talks a lot about this kind of maker projects. So this is his term, and I've stolen it. But the thing that I really find interesting about this, and the idea is of moving it over to software, is although it might be initially intimidating that you've got all this choice and all these possibilities, and that might scare you a bit, once you start really start using it, that cognitive load really does reduce very, very quickly. And the great thing as well is once you've kind of used it a bit, if you go away for 2 months and then come back, you're not wondering where you've kept tools or where you are in your workflow, because it's all there in front of you, first order. It's very transparent, the functionality. I know exactly how many hammers are on that wall by counting them. I have no idea how many hammers are in the toolbox on the right. So in that sense, it's very easy to find the right tool the first time, because all the tools are laid out. This inevitably improves productivity and hopefully improves creativity. On the right-hand side, it seems like it might be simple, but a lot of the functionality is hidden. This can lead to a high cognitive load if you don't use the software regularly. Then every time you use it, you have to relearn it. Certainly if it's command line and that the options are just not easily accessible, you have to go and read some web page somewhere in a manual to type in extra options into a command line prompt. That's not very useful for somebody to play with the software and really try and learn how to use it on the fly. And it can get really frustrating. So I really wanted to kind of go with this kind of bite the bullet, with it being initially quite intimidating, but hopefully when people start using it, they'll realize it's not actually that complicated. And that's where the clickbait on LinkedIn came in, where ultimately, because my other passion is electronic synthesizers, and I took a lot of inspiration, somewhat subconsciously, although partly consciously, as you can see from the color scheme. 1970s analog synthesizers very much had to be first order accessible because they had no choice. There was no digital components. But they did a very good job at laying out those analog dials and functionality in a very clear workflow. And the great thing about knobs is that you know exactly the range of values that can be used. And also the kind of the calibration or the resolution of each knob gives you an idea of the reasonable range of values that you might be looking at. So it guides the user into using the knobs in a real useful way. And it just makes it a little bit friendlier and a little bit easier to use. And I suppose the proof's in the pudding that certainly the first Moog synthesizers from the 70s have been remade multiple times, and you can still buy them now. And they dominate the synthesizer world as much as the digital alternatives, which maybe have a very much a menu dive-in approach to making music. This is, in my opinion, a far more creative way of approaching this kind of subject. So, find a couple of slides. One thing I'm very conscious of, in certainly when we think about the bioinformatics side of metabolomics, is it's very, very easy to rely on software and then not have your personal accountability. It's very easy to use the standard settings on XCMS or the standard settings on Compound Discoverer, or use a QC correction algorithm where it's one line and it's basically run QC correction and you just accept whatever it produces. But when you trust in technology and trust in other people's algorithms on your data, and remember, your data isn't the data that they designed the software for necessarily, you are not being accountable personally. And if you're interested in this subject, it's not a science book, it's more into politics and government. But the idea of accountability, I think, is becoming really important, particularly with the advent of AI and getting AI to solve a lot of your problems. I really wanted to make this software so that you could learn how to learn and understand the theory behind the software, so that you can then be accountable because you know exactly what the software is doing. And the other thing that I've really lent into is this idea of experiential learning, where you experience the software, you reflect on what it's doing, you think about how it's functioning, you then maybe change something, and then you experience how that change affects the data, you think about it, and then you go round and round in this loop. And by creating software tools which enable experiential learning, I think that people can then be more critical of their own data, understand their own data even better, and ultimately become accountable before they go on and do the statistics, which hopefully is accountable too. And that was the last slide. So on that, I will end, and I will hand it back to Rasmus. Thank you, Rasmus.
Thank you so very much, David. This was absolutely excellent. I assume there will be some questions. Maybe you can just raise your hand if we already started. Jan, maybe you can just ask the question, Jan. That's perfectly fine.
Yeah, hello. Yeah, so my question is, you showed that you are fitting on the QC samples always, but if you just fit through the QCs, your RSD, the D ratio, everything will look better the more you overfit. So how do you actually do a fair assessment of this fit, if it's any good or if you're just overfitting?
Well, as I showed,
yeah, sorry.
Well,
also, if you compare methods, you need some kind of metric to see what is actually fitting best.
Yeah. So as I showed in the slides at the start, and probably showed a bit too quickly, the algorithms optimize using cross-validation, and there is the option to have reference samples in there. I could have shown you a data set. There's a second data set on the GitHub page where it's got reference samples in there that you can then project through whatever correction, and the statistics for those reference, so the RSD and the D ratio for those reference samples gets saved out into your export file along with the QC RSDs and the sample RSDs and the D ratios. So yeah, you can do it. Or if you really don't believe that, if you think that it's overfitting, generally if you constrain it reasonably well, the cross validation works pretty well. I've used this a lot, and but reference samples are great. Remember also, and this is a big thing, confidence intervals are really important, because if you're correcting to 5 QC samples and then you've got 4 reference samples, the measurement of that RSD is not necessarily going to be the same because your sample size is so small. So you're going to have to look at the confidence intervals of both and see whether the confidence intervals are overlapping. So that's something that I introduced in a later version of this software, just so that people get a real idea that when they start quoting RSD values, that they're not very accurate unless you're using 20 plus QC samples across an experiment.
Daniel is asking, well, he's saying awesome talk, I agree, but how many QCs are optimal per batch, he asks. Yeah, that's a good question, I guess.
Yeah, it's how long's a piece of string question. It depends on your platform, on your form, technology, how good your methodology is. When we first started using this back in whatever the date was, 2014, on the HughesMet project, it was shocking how much nonlinearity and how much drift within a batch was there. So we put a QC every 5th sample. There's a trade-off. Obviously, the ideal would be every other sample, but then your experiments are going to be really, really long. So there's a cost, and there's only so much pooled sample that you can produce. So there is an experiment out there to be done, but it's going to be very much dependent on whether if your method's very, very good and you don't have very much nonlinear drift and it's very linear, then you don't need the frequency to be quite so high. So back in 2004, we had it very, very high, but now the methods that I'm seeing now, certainly from the same labs, if you like, that I was working with. So I worked with Rick Dunn back then, and data that I see from Rick now, the methods are so much better that the drift is so much more linear that you could get away with 1 in 10, 1 in 15. I still like to do the 1 in 5 because I'm a statistician. I want to see enough QC samples that I can calculate an accurate measure of RSD. So I like a lot, but I understand the constraints.
Thanks, makes sense. Flavio is asking in the comments, what's the structure of the data in the CSV file to feed to the software? And do you label the groups of samples too? Do you find the chat?
Yeah. I still share my screen. Can you still see my screen?
No, we don't. Sorry, we don't see your screen.
All right.
We see you.
Share again. Gosh, I think I've lost how to share it. On the very start of the slide 4, I gave a quick overview of the data structures for 2 table data structures, flat text, CSV or an Excel sheet either. Each column is a metabolite. There's also columns which are sample site or the batch class. If you go to the
audio. David, there's a problem with the sound.
Oh. Weird.
Yeah,
You've got a bit of an echo and oscillations.
it's true. The sound is bad. Let me just remind you that it's being recorded, and it's being recorded by David. So the sound is going to be fine eventually on YouTube when we put it there. But maybe it's. Can you try and say something again, David?
Yeah, can you hear me?
Yeah, we're getting the echo from Australia.
You sure it's not because somebody else's mic is to do?
I don't know. It sounds like you have a synthesizer going, actually. It's a huge chorus.
Yeah. I can't. I don't know how it could possibly be accurate or something there.
Maybe try and set the up in the upper corner. There's something called original sound for musicians. If you turn that on, maybe it changes something.
Audio original sound. How about that?
Same thing to me, at least.
Right, I'm going to change to my. Any better?
Much better.
Okay, there we go.
Yeah, that's good.
Very good. Maybe we repeat the answer then, if it's okay with you, David.
What was the question? Oh, the data structure. Was
Yes,
I
yes.
echoing all the way through my talk?
Yes.
Oh, should have said.
No, not during the talk, just in the
Not
last few
all right,
questions.
just now. Okay, fine.
Oh,
go.
no. Oh, sorry. No. All is good. All is good. We're basically just
I
missing
thought
the last.
everybody just sat through 45 minutes of echoes.
Can you repeat the presentation,
Yeah,
please?
I've got a special thing. Yeah, sorry. So you were talking about the data structures. You can ask it again if you like.
Yes. So what is the structure of the data in the CSV file to feed to the software? And another question, do you label the groups of the samples too?
So I did very briefly mention this right at the start of the talk. It's based on two tables. One's called a data table and one's called a peak table. The peak table includes all the information for each peak or each feature, like metabolite name, metabolite formula, molecular weight, retention time, and then it will have a unique ID. And that unique ID will be a column in the data table. Also a column in that data table will be a sample ID, a sample type columns, which can either be a blank QC sample or reference, an order column, which will be a numerical order of injection, a batch column, batch number, and then you can optionally put your case control, age, whatever else are the metadata, but it will only operate on those four things: sample ID, sample type, order, batch, and then each of the metabolites. If you go to my GitHub page, there's examples. You can just look at an example. But it's very, very straightforward, flat, tidy data.
Yeah, good. Thanks. Another question from Federica. Great talk. I have a question about combining data sets, e.g. if we have additional samples that were not part of the pooled QC, is there anything we can do, or do you have a reflection on this?
So I know people do. One way to do it, if you would like to do it, is you would have to make sure you make extra QC or have what is known as a long-term pooled QC, which you might make in a giant batch somewhere else, and you might use that as a reference sample in my correction software, for example. My personal feelings are that you can't join data sets together. If you look at that other talk I mentioned about, the one already on YouTube, if you search for it, the problem is that if the sensitivity of the instrument changes between experimental runs, even if you have a pooled QC that's the same, if the gradient of a particular metabolite changes, I'm trying to do it with my hands, then the variance of your response is going to be different. So when you can align the QCs, but you can't correct for the difference in variance. So the only way you can do that is to have some sort of calibration at the start and end of each batch, and then you could correct the variance as well as the mean as the shift, and that would be a possible way of doing that. But the one big flaw of this method, well, there's two big flaws. One, it's dependent on the assumption that your pooled QC is repeatable across the whole experiment. That's the biggest assumption. And that your correction is additive, not multiplicative, when you've done a log transformation. So that correction, that linear kind of like additive correction, is going to be the same for all the samples. It doesn't have to be amplified. I didn't explain that very well. If you go to my talk, I talk about that whole thing for like 45 minutes.
Nice. Thanks. Victor's asking, great talk, great job. Oh, I lost it here. Sorry, many comments coming in. Let me go up. Have you considered including QC dilution series in the software? For instance, filtering variables depending on their slope and RSD of the slope across sets of serially diluted QCs along the sequence.
Yeah. So who was that?
That was Victor Gonzalez Ruiz.
Victor just answered the previous question. So that's what you would need to do. We have done that on a couple of occasions. More recently, I haven't included it in this software, but you can. That would give you the best data. In that, if you were to do a dilution curve, the problem is the dilution curve can only go negative, so you can only go below the QC, not above the QC. So you'd have to think of a way of going around that. That's not so difficult to do with urine, but with serum, not so easily. But yes, if you do a dilution curve, then that'll give you an idea of that calibration and that variance, so that you could correct to the calibration and assess it as well from that calibration.
Yeah, makes sense. Jan is asking, do you have any thoughts on the dilution that happens when you create a QC sample? For example, a compound that is practically only present in a subgroup of samples might have a low concentration in the QC and thus not be measured well.
Yeah, it's a method that's built around the concept of a pooled QC. Now, I've very rarely seen it where it would have to be very low concentration in the majority of the samples for it to. But even then, it gets dominated by whatever the big. So a good example would be if one person is taking a large amount of a single drug. When you do the pooled QC, you will see a very good QC trace, but you'll only see one sample, and that'll be the person on the drug. Because when you do the pooled sample, it's still there. It's diluted down, but it's still massive. So yes, it is possible, and that is true, and that is a limitation. I've discussed this with several people, and if you were in the business of looking at rare event metabolomics, where it might be that you only see a metabolite in a small number of the injections, then this method's not for you. But then equally, why would you want to correct concentrations? Because basically you would be looking at a binary signal. Then it'd be like, is it there or is it not? Rather than the quantification. That's the way I would approach it if you're looking at that kind of style of metabolomics.
Makes sense. Ilenia is asking, can I process batches acquired at different times, such as years?
Only if you've got the same pool QC.
Yeah, that's a problem.
And then you've got the issue that if you've got a pooled QC that's been stored at -80 for several years, then that will have degraded by the time that you run it, certainly for a number of metabolites. So you'd be very lucky to get a good response. Personally, I think when you start looking at data sets that are run over years, or even I've seen in my time, I've seen even with NMR, which is supposed to be extremely stable, so as an experiment repeated 3 months later, completely different concentrations. So for me, you do each experiment and then you do meta-analysis on the results. You don't try and join data together because I just don't think you're going to win doing that.
Thanks. Bego is asking, hi, David, thank you so much for the talk. I'm starting to use QCMXP, and my question is when you observe some differences in the Q samples from the different batches by PCA, by intra-batch is okay? Okay. Which method would you recommend to correct the batch effects?
Not quite sure I'm understanding the question, because it's kind of done it automatically. Maybe he can email me and I can help him out.
Right, I think that's a good idea. So if you can mail David, then take it from there. I think that's a good idea. Any other questions? Can I ask you what is missing in your software? What would you like to put in there?
I think somebody's already mentioned it. Doing that calibration, being able to, if I so rarely come across people who do, my lab's done it once and now I close my lab. I now outsource my metabolomics to Metabolon. So I don't actually generate my own data anymore. But I do analyze a lot of other people's data, and it's very rare that somebody will give me data with that calibration curve at the start and the end of each batch for me to develop software so that I could get something that I knew worked consistently across different labs. That would be the thing that would be the missing thing.
Yeah.
It will scare people to death, though. When I show my software to people that do very big studies, so like 10, 15 batches, it's scary how bad the data can be. And if you start adding in the calibration, things that at first look okay, suddenly. So it's very scary. So hold on to your hat if you want to start doing that kind of stuff. But it would be lovely to add that in.
Yeah, okay, makes sense. We have another question from Raphael. Hi, David. David, when intra-batch variation is assessed using pooled QCs and inter-batch variation with a reference material, large metabolomic study, you'll likely encounter features in the RM that are absent in the QC and vice versa. What happens to those?
I don't. My software doesn't. My software uses the same QC for the within and between, so I don't use a different. I have the facility, and I didn't talk about it in the talk, where you can correct by sample, which is basically it ignores the QCs and then just tries to fit in a regression. I put it in there just so people can see how bad that is when they actually look at the QC, because you would think that would be the best thing to do if you just thought about it naively. But the problem is that unless you can guarantee that the variance in each batch is identical, you start doing that correction and it looks really nice in a PCA plot, but it's not right. So you can try doing that, but I don't have that. I could very easily put that in where it corrects between the batches on the references. Don't think it does at the moment. Yes, but if you did do that, yes, you could find features that were not so great with one or the other. But that's where the filtering works. The filtering's done across all the batches, or the statistics are done for each batch and then across the batches. So it'll all come out in the wash. If something's bad, it'll get removed, whether it's bad within or between.
Right. I have another question. You said that the data has gotten better over the years, and you are using less QC samples than you used to. But and you don't really want to say how many QC samples you want, but how few would you be willing to do?
Well, put it this way: if I could show you an example, I'm not going to because we're going way over time. It'd be love to show you. So we as I was mentioned earlier, we started using Metabolon. Now, Metabolon do really thorough QC. They do QC injections, but they don't give that QC data to the client, which I don't like. Keep asking them, doesn't happen. So what we did in our first experiment with them is, without telling them, we put some pooled QCs in to the samples that we shipped to them. We put 4 QCs distributed, and just to see how good their software was. If they're not going to tell me what the QC is, then you don't tell them, you put some in. And it turns out that their data is fantastic, so they should be releasing it because it's only going to make their data look good. But the thing, when I looked at doing my QC correction, I've got a limiting factor that if there's less than 5 QCs, it won't try and fit a spline. It won't let you, because there's too few samples to even attempt. 5 is still poor, but it won't even let you. So that if you've got less than 5, you can do a linear correction. So that's the limiting factor for me. 5 I'd like for the statistics, so you can get a fairly reasonable measure of the statistic. And also, if you want to do correction, then you've got to have enough to be able to model.
Makes sense. And to trust the cross-validation.
Exactly, yeah.
Yeah. So Raphael has a follow-up, but the software on the reference material issue, but the software has an option for inter-batch correction using a reference sample. Such
I've
just
realized that I did actually put that. Yeah, and it's fine. I mean, what was his query? Sorry, if we
yes. So sometimes you likely encounter features in the reference material that are absent in QC and vice versa. And what happens to those features? Are they excluded from the analysis?
Well, they will be, if there's not enough QCs within a batch, then it will be filtered out because that pre-filter will reduce. The primary correction is on the batch. The reference between, if there isn't a reference, I think it will do nothing. So it won't correct at all because there's no reference sample. And then if it's okay, then it'll keep it based on the statistic across all the batches. And then if there is and it corrects it okay, then remember that the overall statistics will be the combination of all the batches joined together. So if the between batch the reference correction is poor, then it will be reflected in the overall QC as well.
Yeah.
If that's not clear, he can email me again and I can go through it with him. But thanks for pointing out a feature in my software that I'd forgot that I'd actually implemented.
And he says thanks, thanks for the awesome software and the talk. So that's nice. One final question from Uyal. Great talk. Can we use this software for targeted metabolomics using a set of internal standards? Do we need pooled QC for normalization?
Has to be pooled because there has to be a QC in every sample.
Yeah. Yeah.
But we have done it for targeted, but it's good practice, even if you're doing a targeted method, to have a pooled QC so that you can estimate that precision. We have used it for targeted very successfully.